Hi, my name's Bob Flynn, founder of Exacta Global Smart Solutions. Hi, I'm here today during Etsy IoT Week to talk about IoT semantics, specifically how semantics is supported by the oneM2M standard. I'll describe what semantics is in oneM2M and why we need semantic support in oneM2M. Then I'll take some time and describe some of the semantic-based capabilities that are described in the oneM2M standards. Then I'll also describe in detail oneM2M's semantic annotation and discovery features. And in the next session, I'll demonstrate these features using the oneM2M CSC implemented from Cordon. In a typical IoT deployment, it can be very hard to take advantage of data or devices that have been deployed for a different purpose than the particular vertical that the device was designed for. This is because the wide variety of design choices that can be used for IoT create a large number of permutations or combinations. In oneM2M, we talk about how the use of the oneM2M service layer enables developers to build better applications that take advantage of devices that span different verticals. oneM2M is a cross-vertical service layer platform that allows application developers to access data from multiple sources and deployments or verticals. It does this by providing an abstraction of the variety of design choices present in the IoT stack. For example, when a developer uses oneM2M, she does not have to address the fact that devices use different communication channels, such as cellular or fixed or Wi-Fi, or different security protocols, or different transport protocols, protocol payload bindings, or device management implementations. And this is because oneM2M exposes APIs that abstract those aspects into primitives that do not need to be aware of the underlying IoT stack for each particular device. Similarly, oneM2M provides an abstraction for semantics. oneM2M supports several semantic-based functions that can be used to help bridge the data understanding across different verticals. Some of those semantic functions are used to be able to interwork with existing ontologies that are used today in deployments. oneM2M also has a base ontology that can be used as a common abstraction. The oneM2M resource repository stores digital representation of devices. We can use the oneM2M generic interworking concepts and base ontology to describe existing non-oneM2M devices such that an interworking proxy entity can facilitate communication between the device and the oneM2M CSC. This exposes all of those devices and their data to application developers using the oneM2M API. The existing devices do not change, and the existing applications do not change. However, we cannot use data across multiple verticals simply by connecting all the devices together. The data needs to be understood both in terms of what measurements are and what they are measuring. As an example, 30 is not meaningful unless we know that it refers to temperature in degrees Celsius. Even then, knowing whether 30 degrees Celsius is important depends on whether it is a measurement of outside temperature or indoor temperature. Ontologies are used to provide meaningful descriptions of the data contained in those digital representations. Just like there are many existing IoT devices with multiple ways, referring to the protocol stacks, multiple ways of communicating, there is also many different ontologies that exist. In earlier sessions, we learned about the serif ontology and the various extensions to the serif base ontology. By using these ontologies, oneM2M gives us a way to effectively use data across different verticals, abstracting the communication differences of devices, providing data model representations, and semantic descriptions of the devices that can be used for discovery, as well as the context of the devices, and finally, the context and description of the actual data from the devices. In oneM2M, semantics of data and devices has been included since release 1 and has continued to evolve since then, starting with resource attributes that can provide meaning, such as the resource name attribute that can provide hierarchical structure to the data, and label attributes that can add additional metadata for understanding and discovery. In release 2, oneM2M added additional ontology support with the semantic descriptor resource and semantic discovery. In release 3, semantics functionality was further developed to add semantic query capability and reasoning and mashup functionalities. Also, in release 3, oneM2M added support for smart device templates. These provide a modular and reusable framework for representing common devices in a hierarchical structure that is well defined. That is how oneM2M breaks down the silos to work across verticals. All of this is supported with the Cordon platform. A demonstration of this using the Cordon platform will be in the next session. So what do I mean by understanding data? It starts when data is first received from a sensor. First is the raw data that we need to be able to interpret. For example, understanding that the received bits of data represent a floating point number. At this level of interoperability, these are generally addressed by the syntax of the systems transmitting the data. But then once we get this data, for example, of a floating value of 20.5, we then need to convey the knowledge that this number is a temperature and that the units are degrees Celsius. For example, in oneM2M, in a oneM2M content instance resource, we can transmit the value 20.5. If we wanted to, we could also transmit 20.5 C. But if an application discovers and tries to retrieve that particular content instance, how does the application process that content instance? Without a way to further describe that data, it is necessary to already have an understanding of what is in that content instance. But even with that understanding, for example, maybe the container resource is named temperature and a label value indicates degrees Celsius. Even with that understanding, we then need to know what this is a temperature of. And then once we know this information for a temperature sensor in one particular deployment, the same process has to be repeated for the next sensor that is detected. These are the semantic aspects of data that are needed to understand and use data across different verticals. This is what we can realize using semantics and the oneM2M base ontology. So now that I've hopefully made it clear why we need to have semantics in an IoT system and why oneM2M has included support for semantics from the very beginning, I'll describe some more of the concepts as they are implemented in oneM2M. And the first thing I'll describe is semantic annotation. Semantic annotation in oneM2M is the process of adding semantic content to resources so that information about those resources can be shared. For example, a oneM2M container resource may contain a semantic description of the data as degrees Celsius, or an application entity, an AE resource, may contain a semantic description of what the device does, such as a lamppost and where the device is located. In oneM2M, the semantic annotations can then be used for discovery and queries based on the access control policy rules. If an entity that makes a request does not have the necessary privileges for the semantic descriptor resource, then the information will not be available for that request. This is applying the same access control concepts to semantic resources that we do for all other resources in oneM2M. Next is semantic reasoning. Semantic reasoning in oneM2M is a mechanism to derive implicit facts, facts not directly stated but rather inferred from other information available in the system. Semantic reasoning can help provide better discovery and query. In the demonstration, I'll give a simple example of reasoning. As an example, I describe a device as being located at a specific address. By placing the appropriate set of triples into the semantic description of that device. Then, in a completely separate resource, I can describe that this particular address is part of a neighborhood. And I can also describe that this neighborhood is in a particular city. Even though these semantic descriptions are separate and not even related to the device, if the originator of this request has permissions for all of these resources, he can issue a query to find devices in his neighborhood or city, and the result will include the device that I described. This is a powerful feature that can greatly enhance the semantic interoperability of different devices and data associated with it. Discovering IoT devices becomes much more rich and meaningful, and this is scalable. The next oneM2M feature is semantic mashup. In some cases, being able to find devices and their data is not enough. Sometimes the data needs to be combined with other data to compute a desired value. As an example, described in oneM2M's TS34, which is the semantic support document, a comfortability index is defined that is computed by combining data from a temperature sensor and a humidity sensor. A semantic mashup can be defined using oneM2M resources that enable the query for the devices that provide the appropriate data sources, as well as a description of the business logic that needs to be applied to the discovered data. This is to yield a result in terms of the final desired output. This process is called semantic mashup, which is supported by oneM2M. Other semantic capabilities that are described in TS34 include ontology mapping, where similar concepts that are described in different ontologies are mapped such that their meanings are mutually understood. For example, a light in one ontology could be the same as a lamp in another ontology. Another example is identifying that a sensor is a subclass of a device. With the many different ontologies that are already in existence, oneM2M supports being able to use different ontologies yet still get the desired behavior. Another feature is semantic validation. When an ontology is used to describe devices or data in oneM2M, then the oneM2M CSE, if there are errors in the information provided, then the oneM2M CSE cannot properly use that information. oneM2M helps to detect user-based errors by validating the semantic descriptions that are provided against a user-provided ontology reference. There are a few other features described in TS34, semantic support. I would refer you to that document for more information about semantics in oneM2M. So let's get a bit more specific. Now I will start getting into the lower level details, which will lead to a demonstration of some of these features. As I indicated a moment ago, the ontology attribute can contain a link to an ontology that defines the required definitions of the semantic information that is related to this particular resource. This ontology ref can be used for validation of the semantic descriptors that will be provided. This validation process is not required, but without it, the CSC will not be able to detect certain errors in the semantic descriptions. A semantic description can be provided for resources in oneM2M that are used to convey data or certain types of functionality. For example, the AE and node resources convey information about a device and its capability. Container, content instance, flex container, and time series resources are used to convey data. And then there's the group resource, which is used to organize devices or sets of data. Each of these resource types can be given a semantic description. A subscription resource is an example of a resource that does not support semantics. There is no practical constraint to what can be described in a semantic descriptor resource. In this example, I provide a description of the smart lamppost. And for that description, I am describing, first what it is. It's a lamppost, and I'm using the serif extensions and describing this lamppost as both a lamppost and a photometer. Also, I'm describing what this smart lamppost does, what this device does. In this case, the sensor aspect of the lamppost measures some properties, and those properties are listed here. They're also extensions of the serif-based ontology. This particular lamppost measures illuminance, luminescence, and phosphorance. I also describe where this particular device is. In this case, it's provided in terms of both the latitude and longitude, and also I'm providing a description of the street where this device is located on, Gran Via. And I'm providing some other useful information, such as the manufacturer, last maintenance date, and properties of the device, or properties of the light. And since the semantic description is a child resource, as opposed to an attribute, we have the ability to create semantic descriptions that can have a desired level of privacy. For example, this lamppost could have a phone service attached to it also, where I want the knowledge of that phone service to be available to everybody, as it is intended for emergency roadside assistance. However, I want the maintenance information to be available to authorized service organizations only. This can be achieved by applying appropriate access control policies to the semantic descriptor resources. The resources that I mentioned earlier that can contain semantic descriptions, a semantic descriptor resource is a child of those resources. Therefore, there can be multiple instances of the semantic descriptor child resources. Now, let's go into details. Let's go even deeper into the details to create a semantic descriptor resource. On the previous slide, the semantic description was provided in RDF Turtle format. oneM2M supports other formats as well, such as the OWL XML, RDF XML, JSON LD, and Manchester. Whichever format is used, when the semantic description is provided in a oneM2M primitive, the attribute that contains the description, descriptor is the name of that attribute is required to be in base 64 format. Additionally, the underlying format used must be provided as well. So let's put all of this together, as this will lead us into the demonstration that I'll be showing of Coordinate's implementation of this. We start with the semantic description of our device. Shown here is the RDF turtle format. For this demonstration, I'll be using XML format. So I converted the previous description using an online tool. This is not necessary, as oneM2M supports the original RDF turtle format, but this is the format that I'm using for this demonstration. As I mentioned earlier, whichever format is used, the payload needs to be sent in a oneM2M primitive in base 64 encoding, as you see here. So putting all of these steps together, this is a complete representation of a semantic descriptor resource. I'll show examples of this in the demonstration. This particular payload could be used in a create request to create a semantic descriptor, for example, as a child of a AE resource or an application entity. Now that I know how to create semantic descriptions for my resources, let's take a look at the benefits that we get from that. I'll demonstrate one of the oneM2M features that take advantage of semantics, the semantic discovery. This is a sample discovery request that I'll show you. What I'm trying to discover here are streetlight devices, where I define a streetlight device as a lamppost, again using a serif extension ontology. Additionally, I want to know about the streetlights, only the streetlights that are located in Tedesco. When I issue a semantic discovery request, I'll be using HTTP requests in my demonstration. Issuing a semantic query uses the get operation, and the target in this example is the top level of the resource tree. I'll then specify that this is a discovery request using the filter usage parameter. And then I'll provide the semantic query that I am interested in. And since I'm using the HTTP protocol, I'm required to %encode the SPARQL query. At this point, I hope to have impressed upon you the value of semantics in the Internet of Things domain. oneM2M has a collection of useful features based on semantics that could be considered essential for full cross-domain interoperability of devices. oneM2M has had this view from the start, as shown by the features introduced in the very first release and further enhanced in every release so far. I spent some time discussing at a high level some of the features that oneM2M has for semantics, and I also went into full detail describing how to try some of those features. I would also suggest that you look at TR45 for a working example of semantics. With that guide and the information in this tutorial and the earlier tutorials about the serif ontology, you have the information needed to try semantic functionality yourself if you have access to a oneM2M CSE that supports semantics. So that sets us up for the next session, where I'll demonstrate semantic annotation and semantic discovery and some semantic query using the coordinate oneM2M CSE. I hope to see you in the next session. I hope to see you in the next session.